So again, our topic for today is week 6, which is the regular language. So this is the finite automata of a supermarket automatic door, wherein there is only exit or entrance. Okay, so we have the front pad and the rear pad. Now, let's try to create the transition table and the transition diagram of an supermarket automatic door. Okay, so this is the transition table. So the states are the close and open. Okay, so again, we have two states, that is only the close and open. So what are the possible inputs? The possible input for the for the transition, we have neither, we have front, we have rear, we have both. Okay. So now let's try to check. Okay. So this one is the transition diagram, or what we also know as the state diagram. So from here, from the state close, okay, so neither, if it's neither, either close, close because it loops into itself. Next, from close, okay, so front input, it will go to the state open. That's why this is open, okay? And then, okay, close, going to rear. Is there any? Yes, because as you can see here, there is a rear here input and it loops into itself, which is the closed state. That's why this is closed. Next, we have another input, which is the both. Okay, so it loop into itself into the closest state. That's why this one is closed. Let's try to check the open state. From the open state, okay, so do we have neither? Yes. We have neither input that is going to transition into the closest state. That's why we have closed state here. From open, okay, we have three inputs here that loops into itself. We have the front, we have the rear, and we have the both. Okay, that's why since it looped into itself, the state is open state. Okay, so this is the state transition table and state diagram of an supermarket automatic door. Now, to give a recap, if you remember, we already discussed the finite on the automaton of a 5-tuple notation. So the 5-tuple notation consists of the Q, which is states. So we have the sigma symbol here that is called the alphabet. This is the transition function. This is the initial state or the starting state. And F is the final state or the accepting state. So again, this is the composition of the 5-tuple notation and it should be in order. So now, suppose that we have a machine problem here, machine 1. So we're using the 5-tuple notation, which is the state, okay, the input alphabet, the transition function, the initial state, and the final state. So now let's try to look at the diagram here. Here's the transition diagram. So let's check it one by one. What are the given states? The given states are we have Q1, we have Q2, we have Q3. Let's check. So again, these are the states. Next, what is the input alphabet? What is the input? We only have 0 and 1. That's why this is written the 0 and 1 in the input alphabet. Now, let's try to create the transition function or what we also know as the transition table. Now, to create the transition table, you have to indicate or write the states, the Q1, the Q2, the Q3. Next, we also have to write the initial state. The initial state is indicated by what? An incoming arrow. So you should put it here. So also in the transition table, you should also indicate the accepting state or the final state. So remember, in the transition table, to indicate that this is the final or accepting state, we are using what? You are using the asterisk symbol. Okay? So it means that if you see these symbols in the table, the incoming arrow indicates that this is the initial or starting state. Once you see the symbol of asterisk in the transition table, it indicates that this is the final or accepting state. Now, another composition of the transition table is the input. So we have two inputs, which is 0 and 1. Okay? So next, let's try to check if this one is correct. From Q1, let's start with Q1. Q1, transition 0 into what? State. As you can see, just follow the arrow or the transition function. So follow this arrow. So Q1 transition 0 into itself. That's why this one is Q1. Next, Q1 transition 1 into what state? So Q1 transition 1 into Q2. Okay? That's why we have Q2 here. So now we're done with Q1. We're going to move on to the state Q2. From Q2, did it transition 0? Okay? So Q2 transition 0, this one, as you can see here. Q2 transition 0 into Q3. That's why we have Q3 here. Next, Q2, did it transition 1? Yes. So Q2 transition 1 into itself. Okay? So that's why we have Q2 here. So next, moving on to the state Q3. So Q3, transition 0, to whom? Q3 transition 0, this one, as you can see here, into Q2. Okay? Next, Q3 transition 1 into, this is the transition 1 into Q2 also. So that's why we have Q2 here. Okay? Next, so next is, what is your initial state? So again, the initial state is indicated by an incoming arrow. If you're going to check the diagram, this is the initial state, which is Q1 or the starting state. Okay? And then next, what is the final state? So final state or the accepting state is indicated by two circles or double circle. So the final state or the accepting state is Q2. That's why this one is Q2. Okay? Now, of course, you have to write it properly. So again, to finalize this one, so we have M1 equals, so define, write the parentheses here. Next is, of course, it should be in order, write the states. So Q1, so please bear with my writing. Next is Q2. Okay, so those are the states. Next is Q3. Okay, then close it with a curly brace. So those are the states. What's the next one? The input alphabet. So the input alphabet, let's write the set. So I have zeros and ones. Okay? Next. What's the next one? The next one is the transition function. So of course, I cannot write the whole table in here. I'm just going to put the symbol of transition function. So next is the what? Initial state. Then I am going to write the initial state, which is Q1. Lastly, what is the F? What is the final state or accepting state? I am going to write Q2. Okay. So that's how you're going to write your 5 to call notation. Moving to the next slide. Okay, now let's check this one by one. So we're using the same diagram, class. So as you can see here, it's the same diagram as from previous slide. So these are the possible language that can be generated through the transition diagram. Let's check if this one is correct. Okay. So from Q1, it transition 1 into Q2. So this one is correct. Yes. Try to follow, class. Okay. Next, from Q2, transition 0 into Q3. So this is correct. Okay. It transition 0 to Q3. Next, we are into Q3 now. So Q3, transition 0 into Q2. So this is correct. So 0 to Q2. So now we are on Q2. From Q2, did it transition 0 into Q3? Yes, that's correct. So we are going to highlight this one. Okay, we are now in our current state right now is Q3. From Q3, did it transition 0 into Q2? Just check the arrow, the transition. Yes, it has a 0 transition into Q2. So this one is correct. Okay, so this is Q2. So now the current state is Q2. From Q2, did it transition 0 into Q3? Yes, correct. Okay, next, let's try to check this one. So 0 into Q3. Now from Q3, did it transition 1 into Q2? Okay, yes, there is 1 here into Q2. So this one is correct. Let's clear the highlight first. So you're not going to be mislead. Okay. Okay. So again, our current state right now is Q3. So from Q3, did it transition 1 into Q2? Yes, this is 1, and it transition into Q2. So this is correct. Okay. Next. So our current state right now is Q2. From Q2, did it transition 0? Yes, into Q3. Q2, 0, Q3. So this one is correct. Okay. Now, our current state is Q3. From Q3, did it transition 1? Yes, into Q2. So this one is correct. Okay. Next, our current state is Q2. From Q2, did it transition 0 into Q3? Yes, Q2 transition 0. This is the 0. Transition into Q3. Okay. And then our current state right now is Q3. So Q3, from Q3, did it transition 1 into Q2? Yes, that's correct. Okay. Next, from Q2, our current state is Q2. Did that transition 1 into Q3? Please check. Okay, from Q2, did it transition 1 into Q3? So as you can see here, this one is a dead end. Okay, why? If you are going to check Q2, is there any transition, a value of 1 into Q3? None. Why? Only transition from Q2 to Q3 is 0. So thus, this is rejected. Okay? So we are going only to accept the language if the given string is started from the starting state or initial state until accepting state, and of course with the exact value. So in case that this one is, for example, let me use my pen. So for example, I change this one since there is no any input of 1 into Q3. Okay? I will change this one into 0. Will it be acceptable, class? No. Why? For example, I'm going to change this one into 1. Is this acceptable? No, because what? Q3 is not a final state. Okay, so the string is accepted if the string came from the initial state and ends in final or accepting state. Okay, please remember that, class. Okay, now let me remove my highlights. Okay, so next, so this one is a second diagram, a second machine, state machine, okay, wherein we only have two states, which is Q1 and Q2. So Q1, Q2. So this is Q1, this is Q2 from here. And then our inputs is 0 and 1 still. We have transition function. And the initial state is Q1, that's correct. And then the accepting state or the final state is Q2. Okay, so this one is correct. Now let's try to check the transition table for this machine. Okay, now the initial or starting state is Q1. Let's try to indicate it in the table. The accepting state is Q2. I'm going to put some asterisks to identify that this is the accepting state. Okay, from Q1, did it transition 0? Yes. From into what state? Into Q1. So this is correct. From Q1, did it transition 1? Yes. It transitioned 1 into Q2. Okay, so this one is correct also. Now, moving to the state Q2. From Q2, did it transition 0? Yes. Q2 transitions 0, this one, into Q1. Okay, so this is correct. From Q2, did it transition 1? Yes, it looped back into itself, so it is Q2. So this is the transition table. So now, W such that W ends in a 1. So this is the language. Let's try to prove if it really ends at 1. So what are the strings that can be can we create using this diagram? Let's try. Let's try to read the string. I have 0. Okay. When it looks back to itself. Next, I have 1. And then I have another 1. A 0, 1. 0, 1 is accepted. Why? I started with the initial and then ended with the accepting. So it ends in 1. So true. Let's try to use another one. Let's try to generate another one. 0, 1. Okay. From here, 0. Transition 1. Okay. And then it looked back into itself. So another 1. Okay. Still accepted. Another one. Let's try. Okay. 0, 1, 1. Okay, from here, transition 0 from Q1 to itself, transition 1 into Q2, and Q2 transition 1 into itself, and then another one, Q2 transition 0 into Q1. Next, Q1 transition 1 into Q2. So these are all accepted. Okay, so meaning to say this is the language, okay, that ends in a 1. Okay? So don't forget about that, class. So next is the machine tree. Let's try to figure out this machine. This one ends in 0. A while ago, this one ends in 1. Now the language is that will end in 0. How? Let's check this one. Let's try to create the 5-tuple notation. So class, please do remember the order of the 5-tuple notation because it should be in order. So again, let's write the parenthesis and the set symbol, the brace. So first is the state. So our states are Q1 and Q2. Okay? So those are the states. Second is the input alphabet or the inputs. Our inputs are what? We have 0 and we have 1. So what's the next one? We have the transition function. Next, what's the next one? What is the initial state? The initial state is Q1. What is the accepting state? The accepting state is also Q1. Okay? So this is our 5-tuple notation for this machine 3. Now we're going to create the transition table. To create the transition table, so we have Q1, we have Q2. Next, let's try to put the inputs. So we have 0, we have 1. So remember, these are the states. Indicate the input initial or starting state by an incoming arrow and indicate the accepting state. So since we have the same initial and accepting, I'm going to put a symbol here. Okay, now Q1 transition. So let's try to fill in the table. Q1 transition 0 into itself. So Q1. Next, Q1 transition 1 into Q2. Okay, now we are on Q2. Q2 transition 0 into Q1. And then from Q2, it transition 1 into itself. Okay, so that's our transition table. Now, let's try to write the accepted languages, okay, that ends in 0. So to write the language, please bear with my writing. So it should accept 0, it should end with 0. So first, we can have 0. Why? Starts with, the initial state is Q1. The ending state is Q1 also. We have an input 0 here, so we can write as 0. Next, what are the other accepted string? I have 0. From here, I have 1. And then from here, since I'm on Q2, my current state, and then 0. So it ends in it started with the initial state and ends with the accepting state. What else? From Q1, I have 1. Q1 transition 1 into Q2. And from Q2, it transitions 0 into itself. Okay? So still, it ends with 0. Let's look for another one. So from here, I have 1, I have 0, and then it looked back into itself. I have another 0 here. Okay, so you can read as much as you can, but as of the moment, so we're going to end it here. So that's how you're going to generate the language created that ends in 0 using this machine tree or state diagram tree. Okay, do you have some question, class? Okay, let's move to the next slide. Now we have the machine fourth. So this is our fourth example. Starts and ends with the same symbol. Okay? So let's try to create this one. I'm sorry. Let me use my erase. Okay. Now, let's try to create the 5-tuple notation. Okay? So again, we're going to start with the states. So this is the parenthesis. Our states are, we have S, okay? We have Q1, we have Q2. We have R1. We have R2. So those are the states. So next would be the input alphabet. So what are the input alphabet? We have A and we have B. Okay? So next is the transition function. So next, what's the last one? Last two, I'm sorry. Initial. What is the initial? Again, the initial is letter S because it is indicated by the incoming arrow. What is the final state? The final states are, so as you can see in the diagram, we have two final states. We have two double circles here. So we have Q1 and we have R1. Okay, so that's how you're going to write the 5-tuple notation of the machine 4. Okay, now we are going to write the transition table for the machine 4. We're going to solve for this transition function here. So let's write the states. We have S. Okay, we have Q1. We have Q2. Okay, and then we have R1. And we have R2. Okay. Let me indicate that these are the states. I'm going to put Q here. So the input alphabets are A and B. Next, what are we going to do? Indicate the initial or starting state by an incoming arrow. Okay. Next, indicate the accepting state. I have Q1. So I am going to put the asterisk here in Q1 besides Q1. Next is we also have R1 as the accepting state. So I'm going to put the mark here beside R1. Okay. Now let's start to read the diagram and create the table from S. Okay, from S transition A into what state? In transition A into, check the arrow, the direction of the transition, into Q1. So I am going to put Q1 here. Okay? Next, from S, I am still in the state S. So from S, it transition B. Okay, check the arrow, the transition, it transition B into R1. Okay? Next, now I am going to move into Q1. So from Q1, it transition A into what state? It transition A, this is A, follow the direction of the transition into itself. So I'm going to write Q1 also. Okay, I am still on Q1. From Q1, it transition B into Q2. Okay? So just follow that direction of the transition. So now I am on state Q2. From Q2, it transition A into Q1. Okay, I am going to write Q1 here. From Q2, it transition B into itself. It looped. Okay, it looped back. So I am going to write Q2. Next, R1. I am going to move to the state R1. From R1, did it transition A? Yes. It transition A into R2. Okay, let me write it for you. Next, from R1, it transition B into itself. Okay, it looped back. That's why I am going to put R1. Next, from R2. From R2, it transition A into itself. So I am going to write R2. Next, what about B? Did it transition B? Yes. Here's the B. Here's the transition of B going to R1. So I am going to write R1. So now this is your transition table. Now let's try to write the accepted strings. Okay. What are the accepted strings here, class? Let's check. So language. So this is machine 4. That's why I'm going to put M4 here. Okay. So let's start. What are the accepted? So I have A, I have B. How did I come up with A and B? From initial, going to accepting or final, okay, that's A. From initial, going to the final, it's B. So thus, this is accepted. Okay? What are the other answers? I can have AA. Okay? Starting A, it looked back to itself. So it's still A. AA. Next, I have B from starting. And then it looked back into itself. I can still have B. B. Okay? What else? Let's check. Let's try to generate other strings. So I'm going to use A again. A, and then I am going to use another A, and then I'm going to use B and A. How did I generate that? From here, A, look back, A, here B, and then A. Okay, that's how I read the string. So what about on the other side? Let's try. So I can put B. I can also put another B. This is the transition of B. It looked back into itself. Next, I can use this transition with an input of A. And then from here, from R2, so it transitioned B into the accepting state, which is R1. So that's B, B, A, B. Okay. So as you can see here, this is what you call, it starts and ends with the same symbol. For example, started with A, ended with A. Started with B, ended with B. Started with A, ended with A. Started with B, ended with B. Okay? So next, so let's try to generate what is the language accepted by the above automata. So we're going to use the M5. So for the M5, what are the possible accepted values? We can have 0. Okay, 0, we can have 1, and we can have 2. Okay? From here, 0, then transition 1 into Q1, and then from Q1, transition 2 into the accepting state. That's 0, 1, 2. Let's try to find another. Let's try to find another one. I have 0, I have 1, I have 2. Okay. Next, it transition again 2 into Q2. Okay. And then from Q2, transition 2 to Q1. And then from Q1, transition 2 into Q0. So those are the possible accepted language of the above automata. There's a lot more. You can try to generate on your own. But in any other way, whatever you generate, it should start from the initial state or starting state and ends with accepting or final state. Okay? Okay, formal definition of computation. So again, we are using the 5-tuple notation that indicates the states, the input alphabet, the transition function, the initial input, and the accepting state. So W is a string over the alphabet. So M accepts W if a sequence of states R0, R1 until Rn exists in Q and satisfies the following 3 conditions. So the following 3 conditions are, so R0 is equals to Q0, and then the transition function. So Ri, okay, So different states. So Wi plus 1, so increment. So is equals to Ri plus 1. So for I is equals to 0 until n minus 1. So the sequence of states or the Rn is an element of the final state. We say that M recognizes language A if A is equals to W such that M accepts W. So a language is called a regular language if some finite automata recognizes it. Okay, so that's why what I'm talking about a while ago. So those are the strings that is accepted by the automata or by the machine is will be from starting until accepting. Designing finite automata. So let W is such that W is 0 minus 1 string and W has odd numbers of 1. Okay? Okay, so we have an example here. We have another diagram. So our states are Q even and Q odd. So the input is 0 and 1. The starting state is Q even. The ending state or the final state is Q odd. Okay, let's try to design a finite automaton to recognize all strings that contain 001 as a substring. Okay, let's try to read this one. Okay, starting state. Let's try. I have 1. Next, transition 0. Next, transition 0 again. Next, transition 0. Next, transition 1. Next, this is a loop, so I can use another 0. And then another loop. I can use 1, a 0. And then another loop, 1. Okay, so this one is accepted by this finite diagram or transition diagram. Okay? So regular operations. So AB languages, regular operations, we have the union, concatenation, and the star. If you remember the sets of operation, we also use the union, the concatenation. Okay? For the union, if you remember, we are using this symbol. So for concatenation, we use the dot. For the star, we are using the asterisk symbol. So x is an element of x is such that x is an element of A or x is an element of B. So concatenation is xy. So x is an element of A and y is an element of B. So for the star, x1, x2 until xk, so such that k is greater than or not equal to 0 and each x is an element of A. So example, I have the input alphabet here from A to Z. So we can also use the good or bad. So A is equals to good, bad, and then B is equals to boy, girl. For the union, okay, we have the sets good from A, and then we have bad, okay, from A, set A. From set B, we have boy, we have girl. So that's how union works. What about concatenation? For the concatenation, so good boy from set A to set B. So we have next, good girl. Okay, next, we have another element from A. So that's bad boy and bad girl. That's how we generate the bad boy and the bad girl. And for the star, okay, for this one, so we always start with the empty set, okay, empty symbol. Next, we're going to write the good. We're going to write the bad, okay? We have the good, bad, we have the bad, good, and then the possible strings that can be generated from set A, okay? So next, so A1 is equal to W such that W has odd numbers of 1. So our states again, we have Q even and we have Q odd. Next, the input alphabet is 0 and 1. Okay? So next, we're going to write the transition function. So the transition function or the transition table contains the states, the Q even, and then the Q odd. Then don't forget to write the starting state, indicate the starting state, and indicate the accepting or the final state. So let's check. From Q even, it transitions 0 into itself, so correct. So we have Q even here. From Q even, it transitions 1 into Q odd. Okay, that's correct. From Q odd, it transitions 0 into itself. That's why we have Q odd here. And then from Q odd, it transitions 1 into Q even. Okay, so next, we're going to write the initial state. What is the initial state? Q even. So this one is correct. Next, we are going to identify the final or accepting state. The final or accepting state is indicated by double circle, which is the Q odd. So this one is correct. Okay? So to write the final tuple, the 5-tuple notation, so equals, don't forget the parentheses. So I have Q even here. Bear with my writing, please. Okay. And then I have the Q odd here. Okay, close it. And then the input alphabet, which is 0 and 1. Okay, next, transition function. Next, initial state or the starting state. I am going to write Q even. Okay, next, the Q odd is the final state. So I am going to write Q odd. Okay, so this is the 5-tuple notation of this A1. Okay,